right, PChemsters, this is Mrs. Vandal bringing you Blankwalle Chapter 15, Section 6, all right? Here we're going to find the H3O plus concentration and the pH of strong and weak acid solutions, okay? Well, guess what? This section is what's so important. I can't tell you how important this is. Keep up, stay focused, ask questions, and of course, always do your homework, do your videos, do your TRO work, all right? If you don't understand something, do it again. Follow along with your calculator. When I say, you know, pause this, do it, I really, really mean it in this section, okay? Please, please, please do this, okay? All right, having said that, so number one, what are the components of a solution? All right, so if I have a weak acid, how do I know, number one, this is a weak acid? I see the double arrows, okay? So if I see a weak acid in solution, what's it going to do? It's going to dissociate, right? But I'll still have some of the HA, the weak acid in there, and I'm going to make some of this, okay? I have all three things in the component. And what if I have water in here? Well, I have water, and then I have some of this, and I have some of this all in my beaker, right? And so what is the effect of adding H plus to water according to Le Chatelier? Interesting question. In other words, what is the effect of diluting the H plus, or diluting the acid? Isn't that adding more water? If I dilute it, what's going to happen according to Le Chatelier? Well, here's my water. It's going to go to the right. It's going to shift right. You're correct. It's going to shift right. That's going to have something to talk about in a later part of this section. We talk about percent dissociation, percent ionization, okay? So when I'm going to talk about that, we're going to go back and refer to this question right here. It's going to shift to the right. And so what does that mean if it shifts to the right? I'm going to make more H plus, aren't I? Yes, I will. I'm going to make more H plus, all right? Look at number 4. If the concentration of the strong acid is roughly less than 10 to the 5th negative, or 10 to the negative 5th molarity, then the self-ionization of water does indeed become a factor. And what does the self-ionization of water become? So water, is there acid in my water? Yes, there is. How much? 10 to the negative 7? Not much, all right? But if I have a very, very weak, strong, or a weak concentration, there you go, of a strong acid, then both of those are going to contribute to the amount of H plus, all right? So it says, consider the major species in a solution, all right? At high concentrations, not number 4, at high concentration of strong acids, the autoionization of water is insignificant. That 1 times 10 to the negative 7th doesn't make any difference to my calculations, all right? So again, for strong acids, the assumption is that the strong acid is completely ionized. And hey, what is the Ka for these acids? I know we talked about that in section 5.4. What is it? It's infinity. All right, so let's look at problem number 20. If you have a strong acid, HCl, and it's at 0.1 molar, fill out the ice table and determine the pH. All right, well, hey, check this out. Before dissociation, here's my 0.1 molar, my strong acid. Afterwards, I have the same amount of my H plus, my conjugate base, don't I? Just saying. Why did I write a BCA, not ice? Why would it be a BCA? Because what? This is a what? Strong acid. It goes to completion, right? Now, on a BCA table, you're supposed to use moles, but if I just assume I have 1 liter, I can use my molarity values too. So here is my values here, and notice what happens. Here's my original HCl, and here is my final H plus and Cl. Notice how they're the same number again. But what is the number that we are really interested in? It is this number right here. Why is that what's so important? Is because that's what my pH is going to be all about. So pH is a negative log of that value of 0.100. And so the pH, hey, go ahead and plug in if you don't believe me. What is the log of 0.100? And then take away the negative, or, you know, multiply a negative by a negative, and you get pH is 1. Let's talk real quick about sig figs. Why is it 1.000? Well, how many sig figs are in my concentrations? 0.100. 3 sig figs. Well, when you deal with logs, the number in front of the decimal represents your exponent, all right? And the numbers following represents really your sig figs. So if you have 3 sig figs here, you need to have 3 decimals, all right? So let's look at problem number 21. So I didn't write out my BCA table. I'm using this whole idea right here. So if I know my initial concentration of my strong acid, how many strong acids do you have? 6. Nitric acid is one of them, isn't it? Okay. So I can say it 100% dissociated. So my original, see that little O here? Original amount of nitric acid is my final amount of H plus. Okay. So if I know that my H3O plus was 0.50. All right, so my pH is 0.30. Why only 2 sig figs? Well, oopsie, how many sig figs are in here? 2. So the 0.30 are my 2 sig figs, all right? But what about the next question? Look how small this is. Now, I'm guessing before we did this question right now that we're going to go through, you'd say, oh, the pH is the negative constant or the negative log of 1 times 10 to the negative 12. Oh, it must be 12. I mean, if I put acid, a strong acid in water, I'm going to turn it quite basic. The answer is no, I'm not. All right. So the question is, what is going to take priority? All right. So here's my HCl. All right. And notice I have this much. Okay. So I have 10 to the negative 12th H plus and 10 to the negative 12 Cl minus. I really don't care about Cl minus. But what about this? Right? 10 to the negative 7th. So what am I going to do next? I'm going to find out how much total H plus I have. Isn't it 10 to the negative 12th plus 10 to the negative 7? Well, watch what I'm going to do here now. I kind of went crazy and I put them all together, didn't I? This is it in decimal form, and look what I get. Does this part right here make any difference? The answer is no, it really doesn't. Hey, let me go back over here. This stuff I can kind of cancel out, isn't it? It is so much smaller, all right, that you're going to get a really kind of a strange number here, aren't you? So now what? Can I take the pH of this? Sure can. The pH is a negative log of H plus concentration. And I didn't get rid of this number, but just kind of go along with me, all right? So this is what I get on my calculator. If I put this whole number and I added those 2 values in, I got 6.777779657, all right? Or I'm sorry, 6.99999. Don't know where the 7s came from. Oh, I do know where it came from. What is that really, really close to? Isn't that pH really, really close to what? Yeah, it's awfully close to 7, all right? So does that little bit make a huge difference in my answer? No, it is 7. So if you have a strong acid, it has a concentration of really anything definitely less than 10 to the negative 7th, the water takes priority of that. If you have a strong acid with like 10 to the negative 6, the water ionization will have an effect of your pH, okay? So I just wanted to show you that this really makes no difference with really 1 sig fig, my pH value, okay? Let's go on. Okie dokie, so a solution is prepared by mixing 90 mils of 5 molar HCl and 30 mils of 8 molar HNO3. Water is then added until the final volume is 1. Calculate pH, pOH, H plus, and OH concentration for this solution. So do you notice what I've put up here first of all? You recognize this? The moles on top of the mountain, right? All right, why'd I do that? Because I need moles of acid. All right, that's just, I just need to know that. Well, I've also converted these into liters. So can you tell me then how many moles of HCl I have? Well, hopefully you know what. What is it? Go ahead and figure it out. Moles on top of the mountain. What do you get? I got that. All right, what about moles of HNO3? Go ahead. What do you get? You can do it. Hopefully you're calculating away. I got this. Hopefully you did too. So now what? I'm going to actually calculate the H plus first. So molarity, I need to know molarity because that's what pH is all about. Well, what's molarity equal to? Moles per liter. I have a total, add these two numbers up, 0.69 moles, and I diluted it to 1 liter. All right, so then what is my molarity of my H plus is 0.69. So now what? All right, I can find my pH, can't I? pH is negative log of the hydrogen ion concentration, which is this, which is 0.16. Remember, these are strong acids. I can do this, all right? So now I can find POH, subtract it from 14, and I get 13.84. And so I have now calculated pH, I've calculated POH, and now I've already calculated H+, I need hydroxide. All right, I can do this one of two ways, all right? So I can do it this way. OH is equal to 10 to the negative POH, right? So I have my POH, so 10 to the negative POH, and I get 1.4 times 10 to the negative 14, or else how can I have done that? I can have done it this way, or remember this, we have our KW divided by H plus will give us our hydroxide also. So our KW is 10 times 10, or 1 times 10 to the negative 14, divided by 0.9, and I get 1.4 times. That's the same number, isn't it? Isn't that amazing? Well, I think I want to stop here for now because weak acids are going to take a whole lot more time. I think it's a good stopping point. So, hey, I'll see you shortly. Don't wait to be great. Bye-bye.